Welcome to our Systems Engineering 501 final project, where we are going to discuss what systems engineering is. Before we do that, we're going to introduce ourselves.
Hi,
Here
my
are
name is
team
Rishi,
members.
and I'm currently studying material science at WPI.
I'm Ed Jackson, and I'm a robotics master student at WPI.
I'm Tom Mulray. I'm a robotics graduate certificate student at WPI.
I'm Sandy Young, and I'm a robotics master's student at WPI.
I'm going to briefly go over our agenda. We'll start out with a brief definition of systems engineering by me, Tom, followed by the life cycle processes by Sandy, technical processes by Ed, and systems engineering management by Rishi.
So, what is systems engineering? Unlike traditional engineering, which focuses on a single area, systems engineering focuses on the big picture. Let's take, for example, a car. An electrical engineer would focus on the electronics in the car, the touchscreen, the radio, the starter. The mechanical engineer would focus on the tires, the suspension, the car's body. Using this example, the systems engineer focuses on the integration or combining of all of the different parts of the car. In other words, the systems engineer would try to figure out how to get the tires built, how to design the touchscreen app, and how to make sure they are all installed and working by the deadline within a budget. The big picture in systems engineering is not only about what should be built, but also how it is going to be built. We talked about the example of the car and all of the different parts that make up the car. But how exactly does the systems engineer accomplish this? We'll go into more detail in the next section, but it's worth noting that systems engineering is all about the process to manage these different parts. Continuing with the car example, some things that systems engineers do to manage the process of designing and building a car are figuring out what types of features the car should have, determining a schedule, testing the car, and making sure the car company can support the car throughout its warranty life. So, systems engineering is the determining of the what. In our example, it was the car and its different features, as well as the how. Moving on to life cycle processes. What exactly is a life cycle process? If we think of the life of each and every one of us, we go through different phases. For example, you all are in middle school, then you will move on to high school, college, and then into the working world. All of those are life phases. Now imagine if we take those different life phases and apply them to a project. Instead, we are going to call them life cycle phases. Now, the phases for a project are a bit different than the ones you or I go through. They are concept, development, production, utilization, support, and retirement. The concept stage is where you think about the idea from a big picture perspective. Next is the development stage, where you take that big picture idea and try to put it into a type of blueprint known as requirements. The production stage is where you would build out whatever it is you're trying to build. The utilization stage is where it actually gets used. The support phase involves anything that you need to make sure your project is able to do what it is supposed to do. Lastly, the retirement phase is when the product reaches the end of its life and must be retired. Let's continue with an example of these life cycle phases.
We'll use the Øresund Bridge as an example to highlight the different life cycle stages. A little background. The Øresund Bridge links the cities of Copenhagen, Denmark, and Malmö, Sweden across the Øresund Strait. It is the longest combination rail and road bridge tunnel system in Europe. The bridge has been an idea for decades, but it was only recently completed. In total, the bridge cost 3 billion euros and took 5 years to build. The bridge is 16 kilometers, about 10 miles long, and is visible from quite a distance. The first life cycle stage is the concept stage. At this point, we have the major new concept, and we want to flesh it out. Since the 1850s, there has been a desire to build a fixed link across the Øresund Strait. Because of various political and environmental reasons, it was never built. In the early 1990s, the idea of constructing a bridge came up again because the countries in Northern Europe wanted to increase trading. Since the bridge would benefit both Sweden and Denmark, the two countries came together and finally gave approval for the bridge to be built. After we have the big picture, we can enter the concept exploration stage. At this stage, we explore the project's design challenges and stakeholder requirements. There were many requirements for the bridge as Denmark and Sweden worked to connect their countries. it needed to support cars and high-speed trains. The Copenhagen International Airport was very close on the Danish side, so they could not build a tall structure that would block air traffic. They also could not build a low bridge, as that would interfere with ship traffic. Different kinds of bridges, such as arch, suspension, and cable stayed, were explored. The idea of a tunnel came up, as it would avoid those issues, but it would also cost more than a bridge. These different ideas and designs need to be carefully considered. Once the possible bridge and tunnel options have been identified with their advantages and disadvantages, we can move on to concept selection and decide which is the best option. Taking all the limitations into account, the decision was made to build a combination bridge tunnel to connect Malmö and Copenhagen. On the Swedish side, they would build a cable-stayed bridge once Malmö did not have to deal with air traffic, and this would allow for bridges to pass and be cheaper than a tunnel. On the Danish side, they would build a tunnel so that they did not block the air and marine traffic. An artificial island would be built to connect the two. This would allow for a combination 4-lane roadway and 2-track railway between the cities. To address any environmental concerns, an environmental leader was placed on the board of directors. If the work is done correctly in the concept stage, we can create a high-level initial concept with risks evaluated, which would help avoid recalls and rework in later stages. This will also be used to generate early costs and for schedule projection. It is important to spend enough time to understand the project and the best solution. In the development stage, we take the big picture idea and translate this into our blueprint, aka system requirements. Now that we have the requirements from the various stakeholders, the development process takes these stakeholder requirements and uses them to create a system architecture and system requirements. The stakeholder requirements were they wanted the bridge to be completed in 5 years, it could not block the Danish air traffic, it could not block Swedish ships, it could not affect the environment, it must connect the road and rail traffic of the two countries. And then we translate these into system requirements that you see here. When the development process is complete, we have a system architecture prototype, formalized system requirements and documentation, and an enabling systems design. The next stage is production, where you build out whatever needs to be built. This is the stage where the Øresund Bridge is actually constructed. There were 3 parts to construction: the bridge connecting Malmö to the island of Peberholm, a tunnel connecting Copenhagen to Peberholm, and the construction of Peberholm itself. There was a lot of clever engineering that enabled all these pieces to be built. The bridge started from the Swedish side and continued for 8 miles to connect to the island. Its construction was done on land, and then the individual sections were carried out to sea to be put into place. Special barges were created, which would carry the pylons for the towers, because the water depth was only 7.5 meters, while the pylons were 22 meters high. Once the pylons were in place and the towers built, then the span was put in place, starting from the towers and moving outward. The construction of the underwater tunnel started from the Danish side and extended for 4 miles to the island. It was done in a dry dock and then floated out into the sea to be placed in position. They were able to stay afloat because all the openings were temporarily sealed and filled with air. Once they were in position above the final spot, the air was pumped out and the tunnel section sank and was guided into position. To build the tunnel and the bridge towers, the seabed was dug and dredged. This excavated material was then used to construct the island, which avoided wasting material and manpower. During the production stage, it is important to continue communication with stakeholders so they can confirm requirements are being met. If they are not, stakeholders can put a hold on production so they can reassess the situation. Most holds during the construction were due to safety concerns. The discovery of unexploded bombs from World War II put construction on hold until they could figure out how to handle them. There was also one accident that required construction to stop and an inspection to determine next steps. The production phase was largely successful. One of the most critical decisions in the project was to choose a certain bridge early on because it would have been very difficult to change the design once building had begun. After construction is completed, the production stage is done, and we can proceed to the utilization stage. The utilization stage is where the system gets used and does what it is intended to do. The Orison Bridge has been operating for 22 years, and from its history, we can say that it performs as intended and fulfills its system requirements. It has allowed motorists and rail traffic to easily travel between Malmö and Copenhagen. Hundreds of millions of car and rail trips have occurred during its years of operation. The bridge also has provided massive economic gain to both countries. Our next phase is the support phase. This involves anything that you need to make sure your project is able to do what it's supposed to do. In this stage, the support activities for the bridge were bridge maintenance and bridge updates. When building the bridge, they made care to ensure that the bridge could be maintained easily. The bridge is equipped with state-of-the-art monitoring equipment across the whole span. There's a computer system that can detect traffic flow and weather conditions, as well as a year-round manned traffic center. The bridge also contains sensors to monitor road conditions such as carbon monoxide, nitrogen dioxide, and visibility conditions. Also, regular inspections are done of the bridge as well. Some changes to the bridge are to be expected once it starts being used. One realization was that modifications were needed to the guardrail bolts. They began to corrode and required cleaning and a new set of washers to operate correctly. The last stage in the system life cycle is retirement. The retirement phase is when the product reaches the end of its life and must be retired. In this stage, we prepare the system for shutdown and take care of any environmental impacts, legal obligations, and disposal of hazardous materials. The Orison Bridge was designed to have a 100-year operational lifespan. It has currently been in operation for 22 years. A concrete retirement plan is not available yet. There are, however, several standards and practices that are used for bridge demolition and deconstruction that can be followed. The Orison Bridge serves as a good example of how to apply system engineering techniques successfully. Using system engineering principles, numerous engineering issues were resolved in conjunction with the social, political, economic issues and environmental concerns.
Alright, we will now be covering the technical processes. Here you can see the 14 technical processes listed. These processes are listed in chronological order, but it's important to note that they do not have to follow linearly. It is possible for them to be happening in parallel, such as a continued system analysis with maintenance. Feel free to stop the video at this point to read the individual definitions. A technical process helps create processes that take decisive action to achieve a goal with respect to established criteria. We will not be explaining each technical process in much detail, and instead will be following a solar car example to get a general idea of how these technical processes are used. Here are the top 3 major players for the solar car development: the Lightyear Zero, as seen on the left, the SYS501 in the middle, and the Aptera on the right. Each have a radically different approach to the solar car design. The Lightyear Zero and SYS501, for example, look similar to a real car, while the Aptera follows a more alien aesthetic. Most importantly, all have solar panels attached to the roof to help charge their batteries and sustain power. What do all these solar cars have in common? As mentioned, solar panels. These panels are used to power their batteries. The battery's energy is converted into torque to drive the car. Additionally, all solar cars will share components with electrical vehicles, otherwise known as EVs, and fossil fuel-based cars, such as wheels, suspensions, transmission, and other components. Now that we have a basic idea of what constitutes a solar car, let's develop a need statement. A need statement clearly defines a system solution to answer an identified problem. We will create the need statement for you as solar cars can reduce the need for charging and thereby reduce pollution and enhance the solar market. Let's dive into this a bit more. The solar panels will recharge the battery while the car is parked outside or driving on the road, which decreases how much charge time is needed overall. This decrease will reduce pollution compared to traditional cars and enhance the solar market, as solar panels are used on every solar car. Now let's look at the stakeholders for the solar car company. A stakeholder is anyone who interacts with the system, in our case, a solar car. Let's loosely break them up into three categories: inside the company, against the company, and the consumers/investors. Employees will make up most of the stakeholders inside the company. Electric vehicle competitors, such as Tesla, can hire our employees or cut costs to force our solar car company to follow. Finally, the consumers/investors are the main source of capital for the company. Our design will be tailored for consumers and to meet the requirements to satisfy investors so we can have their continued financial support. Let's now move on to identifying how the solar car works. We can look at it as a system of inputs and outputs for high-level functionality. The solar car interacts with four main external factors: the user, the electrical power supply, the environment, and the battery and solar research sectors. The user will be the most intense element, as this is you and me driving the car around. When we think of driving a car, we input controls such as pressing the brakes or turning the wheel. We also receive information back from our car, such as the car's health, or heat/cool air, and maybe even energy if we want to charge our phones. The electrical supply, on the bottom, is assumed to be a standard wall outlet, but this can technically be anything. This is what recharges the car, besides our solar panels. The environmental element, as seen on the right, has environmental conditions such as rain, sleet, hail, or humidity that affects the solar car's performance. Additionally, if the car crashes, then there will be debris left in the environment. Finally, the battery and solar research sectors can provide optimizations to the solar car hardware that make it more efficient, so we have a data line to indicate this relationship. Okay, great. So let's fill in the solar car bubble so we can see the interplay with our inputs and outputs. We won't follow everything, but let's at least analyze the user control input on the top left. The user controls need to be understood. So the input is first decoded and split into changing the car's direction, changing the acceleration, or adjusting the heating system. This information is fed as data into the system display, which is indicated back to the user. We can see that each process, the internal rectangle, has at least one input and output. If we do this for every single process that we've listed, we can see that what we've created is something called a functional block diagram, which establishes top-level functionality. This enables us to develop some solutions to fit into these processes. Now, the candidate architecture addresses the operational, functional, and performance requirements with respect to stakeholder concerns. We'll cut to the chase. The biggest stakeholder concerns are cost and efficiency of the solar car, so let's relate it back to the functional diagram, or the functional block diagram. The most important functionalities of the solar car are solar panels, the battery, and system display. This is supported by the functional block diagram, as we can see on the bottom. Now we must identify solutions for the solar panels, battery, and system display that balance the cost and efficiency, or the stakeholder concerns. We want to create solutions that minimize and maximize the efficiency of the car. We want to create solutions that minimize cost and maximize the efficiency of the car. We won't go into detail of how we do this. We just want to establish the roadmap we needed to get to this point. So now, let's just assume we've created a solution that balances the cost and the efficiency pretty well in your working prototype. So, the systems analysis of the car will be to simulate or model parts of the car to optimize their performance. For example, we want to minimize the aerodynamic drag to maximize the power efficiency. This means if we reduce air resistance, we will get more bang for your buck in terms of energy and the distance we can travel without running out of power. We can utilize ANSYS, an advanced engineering modeling tool, to simulate how the car will travel through air and carve a car shape that uses the least amount of energy to push through the air. Continuing on, let's look at the implementation and integration. Implementation realizes a specified system element, such as building or purchasing hardware or software. Integration will synthesize a set of system elements into a realized system. Now below are two solar cars, the Lightyear Zero on the left and the SYS501 on the right. I've highlighted the solar panels in a red circle for clarity. Now the Lightyear Zero has a created a custom manufacturing process to develop an incredibly tailored solar panel that can only fit on their car and their car alone. Meanwhile, the Sonosian, on the right, purchases existing solar panels units and slaps them on all over their car. We can see these as the little rectangles. Purchasing the solar panels may be a cheaper solution, but it could result in less efficiency. However, a cheaper design could mean more people could afford the car. So, in this example, we see two different ways of implementing and integrating solar panels. Verification is evidence has been provided that system elements meet requirements, while validation is evidence is provided that a system will achieve its intended use. It's a subtle difference, so let's explore it more. Verification is comparing our design to some criteria, such as the minimal aerodynamic drag or solar panel efficiency minimums. For example, let's say we want our car to have a solar panel. We want all of our cars to have solar panels to be at least 15% power efficient. Verification would be ensuring that all these cars produced meet this minimum criterion. Validation, on the other hand, means that the car will operate as a car. So a very popular example is crash tests. While crashing is not intentional, it certainly must be considered as a use because accidents are unavoidable. So validation of safety will create baselines for success through evaluating crash tests. Operation, maintenance, and disposal are the most intuitive technical processes. Operation defines how the system is used. For us, this is driving the solar car around and recharging it when necessary. Maintenance defines how the solar car will be sustained. Tesla, the most popular electrical vehicle company, developed a unique repair shop tailored for their vehicles. Our company, the solar car company, could with sufficient funding follow a similar pattern to repair our cars. Finally, disposal describes how the system is removed. A solar car contains many different elements, so the disposal would have to be careful to deconstruct the car, recycle what's possible, refabricate other pieces, and resell the rest. So what have we learned? Technical processes help evaluate our system with respect to the needs statement, stakeholders, measures of performance and effectiveness. We utilize a holistic and systematic approach to identify the top-level functionality of our solar car. This means we moved from top-down while constantly seeing what's interacting with what to create an optimized and balanced solution. Finally, this set of processes is not unique to the solar car, and they're utilized everywhere. Now finally, Rishi is going to talk to you about systems engineering management.
This next section will discuss systems engineering management. Within a project, there will often be several processes that are not related to systems engineering. For example, project planning, tool preparation, financial management, etc. There are, however, several that do overlap with systems engineering, examples of which can be seen on this slide, including planning, risk management, configuration management, etc. These will be discussed a little bit more in future slides. Planning is probably the most fundamental and important early process that you need to perform in a system. It basically allows you to follow a very disciplined process and use the available tools that you have to plan out this full scope of the project, and to some degree the entire system as well. This might include identifying objectives, key events, key pieces of work that are needed for the system to function properly, scheduling how the development of the system will go, making a budget for the materials that you might need and time and effort, making sure that you have a plan for the management of the system, especially in the systems engineering in particular, risk management, which is very, very important, and also how to configure the system optimally. Assessment and control is primarily about checking in on the different stages of the project, making sure that they are all following what the plan has laid out for them. And if there are issues, then they're bringing them up to the appropriate project leaders so that they can be addressed. This usually also means checking in at all of the checkpoints as well for the project. Example of some of the checkpoints you can see on the bottom left. This is a V graph, and you can see that there are requirements and basic needs for the system on the left. And as they are produced, they basically are verified on the right side. And that's quite important to make sure that everything is going as planned. Additionally, communication between group members is also really important for this to enable really good workflow for the entire systems engineering group. Risk management is, again, another one of the really important processes that a system engineer works on. We define risk usually as a possible problem and then try to see what will happen if they actually occur. So how bad are they? And how often do we think they might occur? This is basically likelihood and consequence. And what we really want to do is remove the risks that have a high likelihood and a high consequence and change them to be low likelihood, low consequence. You can see this on the image on the right. We really don't want risks that are in that top right corner where it's red, where there's a high consequence if it does occur and a high likelihood of it even happening. We want to move it down to the green area. So it's really not a big deal if it occurs, and it's really easy to work around, but it's also less likely to occur. Measurement is where you take the quantitative analysis of the system and evaluate it based off of that. So it's much less these qualitative description of how the system will operate and what you will do, and more actually getting down on the ground and identifying what is working and what isn't working in the system. These are oftentimes done with physical measurements like basic lengths and weights and masses. It could also be time, for example. How long was a process taken? Is that falling within the specifications that were planned out originally? This is basically a good check to make sure that the system is working as planned. Decision management is basically how the requirements, design choices, and risks of the system are all interconnected. This will be a group that is able to look at these different categories and ensure that they are working together in harmony and the system is not failing and faltering because of some imbalance between these different things. And lack of communication, for example, is a really big one. So a configuration management is essentially there to control and create requirements, documentation, and drawing, which is basically essential, especially in the planning phase, but even further on, as changes will occur in the system and in the project, these are really useful to enable that change and make sure that it's occurring seamlessly, smoothly, and with minimal impact on the time schedule of the entire system and project. It also is useful in trying to help find and prevent hidden risks, things that you didn't necessarily consider before, but now starting to become a little bit more important. Information management is all about how you deal with the information of the system. That includes organizing it, storing it, making sure it's secure from any outside threats, and also making sure that it's accessible to everyone within the system who needs it. And this is usually done to facilitate the integrity and security of the different lifecycle stages. It's very useful to make sure that you know how the information is going to be controlled within the system, and you have to evaluate it consistently throughout the entire lifecycle of the system. Quality management is basically the final step in this whole system. And in terms of a project, it's one of the last things you need to do. It kind of makes it a really important safety gap in a system and project. It basically ensures that the processes were all followed and that quality requirements are met. What this means, and you can see an example in the bottom right, this person here is measuring a final and complete part. He's making sure that all of the measurements and specifications are correct according to what the customer required. And you have to make sure that you deliver what the customer needs, of course. If there's changes that need to occur, then you can use this to determine what those are. And this is why you can, and how you can create policies to ensure that the project is meeting the effectiveness that is required. Over the course of this project, we have given broad definitions for systems engineering and its methodology. We have discussed the different aspects of the system lifecycle through the Orson Bridge project. We have discussed the technical processes through the example of a solar-powered car, and have gone into some of the details of systems engineering management for things such as risk and planning. Thank you for listening. We hope you've enjoyed. If you have any questions, we'd be happy to take them now. And finally, here are our references for this project.